Hello everyone. Today, in lecture 15, I would like to start to give you a sense of what disentanglement means in our mind and what is its consequence, okay, which is presumably to produce the observed yielding behavior and possibly strand localization. And subsequently, I will move on to the chapter 10, which describes further about strand localization, mainly in geometries dominated by shear, and describe particularly the case of strand localization at the die entry. I will also inject some comments about the theoretical implications when such a strand localization is observed in die entry.
All right. We're at a turning point. In other words, I think I cannot further delay giving you guys some sense of why we're dealing with something that's not homogeneous, right? It's not homogeneous. We talked a little bit about it. I have been trying to delay any discussion about the molecular origin of what you observe here. Gradually, we should confront the issue of why you could have such a case, like what is shown here in oscillatory shear, right? You can see it's quite complex. It's a nightmare for anyone who is using a rheometer, because without the movie, you were thinking this thing is doing pendulum-like motion homogeneously, back and forth, okay? So the people who sell you the rheometers got a little concerned. I'm making half a joke. They said, Jesus, don't show them this movie, because they will blame me for giving you a rheometer that you cannot do very much with. In other words, the rheometer is when you use a rheometer, you assume that the deformation is homogeneous. Otherwise, you cannot make a proper measurement because you cannot even prescribe, or describe what is going on in your sample. So I would tell the manufacturer of a rheometer, says, don't worry, it just means you need to have a accessory that allows you to see what's inside. It's not your problem, it's the problem of the material, obviously, right? So this is really a good point to do a little review of where we have been, so that we can proceed, because the next topic will be another example of this kind of madness, and this will go on for a while. For example, let's take a look at the agenda we have. We more or less covered most of the topics in chapter 9, including giving you the background of why we start to look at particle tracking, and conditions for having bending, and even conditions for not having bending. We talked about it. However brief that is, we talked about it mathematically. It's clear that when this is much smaller than 1, you will not have shear bending. And this is not external, meaning it's not at the wall, but rather something we can see or perceive that you have slip internally. If that slip is a large amount compared to V, then the system has the possibility of choosing such a state, or choosing a big part that's shear very fast and the rest shear very slow. Who knows? When you saw the movies, it's not something we can predict. So let's, I guess, get a little bit into why this is all possible. because I not only want to show you that this is possible in this simple shear, but it's possible in general, meaning in any other mode of deformation. So in that sense, let's go back to this object, which is what we're dealing with. The movie you have seen is essentially something of this type, magnifying a million times, except when it's in solution, it's in a little more peculiar form. The chains are not even touching each other if you are in a solution. There is solvent between them. But generally, the effect of uncrossability is still there. Okay? It's still there. So, the real story is it doesn't matter what you do. Of course, right now we are doing shear, so you have a sample like this, where as you appreciate, the relevant thing to speak about is watching what's going on at different layers. As I said, this is a millimeter. So they are really about, you know, if you know that your coil size, or I should get you familiarized. After some homework you have done, we keep using the so-called entanglement spacing, which is really when you try to depict your entangled polymer as a network, we are recognizing that there is a building block, which is this subchain. In other words, it's part of this red chain. And as you know, it has a molecular weight for that subchain on the average of ME. And to say that you have a lot of entanglement is to say you have many of such strands. Yeah? A chain that goes to a certain limit. And in the language of what we need to know, this is molecular weight. You can speak about this strand. When you blow it up, in your mind, you should really envision this strand is still very much like a coil, okay? A Gaussian coil. So you can speak about how many cone lengths in such a coil. And then this end-to-end distance of this strand, we call it entanglement strand. It would be an easy way to call it, entanglement strand. And in the literature, one often is called entanglement spacing. It all means the same thing. It is referring to this building block. And then by definition, being Gaussian, this is nothing but NE cone length. So that's Gaussian chain property, right? The end-to-end distance square is linearly proportional to chain length. And NE is just the number of cone length in an entanglement strand. So we actually last time in a homework indicated that this is from polystyrene to polyethylene is something from 3 to 8 nanometers. Okay. So if you take it as 10 nanometers, how many are them in a millimeter? A million already. Okay, it's a million. It's a million of these building blocks. grabbing onto each other because they cannot cross of the individual chains. And a million is a lot. It's already rather hard to imagine. So, but there are a million of this. Therefore, there are a million of these hooks that I'm talking about. So, may I be my guest? This is just keep going. I think this is a picture I prefer. If you have something different, that's fine too. I don't know of alternative, but essentially it should be something of this nature. I know I'm drawing. Obviously, I use black, but it could be all different chains from. A million of them from bottom to top, and of course, this dimension could be 10 millimeters. Then there are 10 million of them from left to right. Right? So keep going. A million this way, 10 million that way. And that's the object you have. And keep in mind when you do startup, right? All of a sudden your speed build up. And let's say if it takes, this is the time for chain to relax. Of course, it can build up quite a bit within tau. How much it can build? Well, it can build Wi amount, right? By definition. Meaning, Wi amount of strand will pass, will elapse. That's the word I think. Well, I think it was you who elapsed. So by the time you reach tau, how many strand elapsed? How many strand has occurred? Wi amount of strand has occurred, right? Right? Because it takes the time it takes to make any strand is this, because remember, this is nothing but, oh Lord. Oh, it's trying to save, that's why. Let me get rid of this. Stop me. I mean, it seems like I'm losing some of you. Can you ask a question if you shake your head? Remember, Wi is tau over T1. T1 is the amount of time it takes taken to make 100% deformation. In other words, 1h to the right. Therefore, after tau amount of time, there will be tau over T1 amount of h to the right. And that's the strand. Shear strand is defined as such. Okay? So if Wi is 10, that means within tau 10h to the right. 1,000, that would mean it would have moved 1,000 to the right. Provided the tau, provided there is no disentanglement, right? The chain will remain hooked. And that's hard to imagine. How can they remain hooked after you stretch it 10 times, meaning Wi equals 10? And by the time of tau, it would have done 10 times. The question, the magical question, by now you should really start to get worried about is, for example, you have applied the Wi. That's literally what we have in the book, in the figure. Let's say you have applied Wi, that's 100. Which means by the time it's 10 of a tau, you have already strand a unit of 10, right? okay? Because Wi equals 100 means T1 is 1/100th of tau. So I need you to be very, very familiar with strain. Strain is just depend on time. So if your the time it takes for you to do 1/10 of a tau, that will be the time, and the rate you have in this limit, of course, is 100 over tau. So that's why it is 10 at a 10th of a tau. Yeah? I don't know you guys like numbers or like symbols. I'm just giving you a case where you have numbers. Okay? Let's say Wi is 100. Then it turns out by the time of 1/10 of a tau, you of course have sheared 10 units by definition, right? The reason I give you numbers is I want you to think about it. And you may say, hey, you may immediately raise your hand. It says, oh, it's only 1/10 of a tau. The molecule, of course, has not moved much, yeah? Because it takes a tau to move. So, it's crucial. So, shouldn't the chain continue to enjoy the entanglement? When I use the word enjoy, meaning continue to maintain entanglement. That's the question. I can even give you a case where Wi is 1,000. Which means what? Which means within 1/100th of a tau, I already shared 10 units. Yeah? Yeah, by definition, come on. Be with me here. And which means, gee, only 1/100th of a tau. That's very short. The chain cannot have moved anywhere yet. By definition, I swear, I raise my hand and says, I will guarantee your chain cannot disentangle. Because this cannot disentangle by thermal diffusion. Because thermal diffusion takes a tau to disentangle. Yeah, to move away from each other. So your reason is, okay, I predict it will remain entangled. Well, I'll come back and tell you, you might be wrong. Something else is happening to force it to disentangle. Well, that will come later. Again, I keep postponing the real essence of so-called force imbalance. What we do know is from the movies, we know under conditions of this, we find, I hope by now you are all very familiar with what is a startup shear. You all suddenly start to shear, you monitor your stress. I'm sorry, it's my habit to save space and oops. Oh Lord, this computer is driving me crazy. I was just trying to undo. Let's see how much we can recover. What did happen? Oh, short. Oh, shoot. Let me see. It's trying to recover, blah, blah, blah. I better try to save it. You see, a bunch of things are missing what we said. but it does not matter. It's recorded, and also computer is mad. I was merely trying to undo. So in any event, what you need to be familiar with is the startup, and I always want to steal some space because that saves you a lot of discontinuity. But you have to tell me which you prefer. So for that startup, you find the stress is building up and reaching a maximum that by now you should be very familiar with it. And remember, I always can freely write this as a function of time or as a function of strength, which is nothing but shear rate times strength. And here I need to be careful when I say shear rate. I should be careful in the previous slides. I should always say, as an experimentalist, what I can control is only V over H. Am I right? I don't have, shear rate is for the sample inside, which in my book I have carefully defined. Gamma dot is always the shear rate inside the sample, which I don't know necessarily. You only know it if you assume, one, no wall slip, second, the shear is homogeneous, there is no shear bending. Only in that limit you can say this, right? Otherwise you don't. I hope I didn't go anything further than what you don't know. And then there's this yield point, and then potentially, well, not potentially, the movie shows that you observe shear bending here. I just want to assure you that this point, for large enough shear, I just want to be careful here. When you have this condition, this point is going with the shear rate to the minus 2/3 power. So this point is shifting to smaller and smaller values, okay, with shear rate. Although the strand is still increasing with shear rate. That's the scaling law that we went through. Okay? 1/3 law. I write it big, but that's the exponent. Right? That's covered in chapter 7, actually. What I wanted to say is that we experimentally observe this point to be something that can be something much less than tau. And that, by now, you should connect what I have said in the past whatever minutes now. That the system is falling apart. At this point, it starts to fall apart, right? Start to break up, right? It's falling apart, not waiting for tau time. It can fall apart much earlier because the strand at that point could already be high. In other words, I know I lost a few things here. In other words, this interaction cannot be maintained. The entanglement cannot be maintained.
I can learn to understand you much better if I...
We know what it cannot be maintained. Beyond gamma y, it cannot be maintained. Beyond that stress maximum. Right? In other words, I propose that the reason, the reason you have this overshoot in here is because this thing cannot be maintained. I don't have to tell you why it cannot be maintained, but you see, in fact, it took us a while to know why it cannot be maintained. The first thing is not, you see, I said this usually in a polymer physics class, but I want to say this again. It's so powerful. We do science by asking what, And that's typically an empirical aspect. And then we now ask how it happened. That's the next level already. And that we call, I have a famous word for it, called phenomenological. In other words, you start to collect information about what in some coherent way. Coherent, meaning in some consistent way, some systematic way. So you start to peek into what features, what laws, what rules you find. And eventually, you really want to know why it happened. And that's theoretical. And that's where we want to be, always, at the end of the day. So you can see by having the movies, there's no trouble. Movie tells us what, and we have some sense of what it means, which is how it happened. Well, it implies this thing goes away. That's how it happened. I'm not going to answer why it happens yet. No need to. You see, no need at this point. No need at this point to explain why it happens for us to understand and appreciate the shear bending. For us to understand when you have a million monolayers, that there could be a horse race. And last time we analyzed the horse race. One horse win, which is one monolayer disentangles, that produce a VS called internal slip. And we can evaluate that slip is, you have a million horses. I mean, God, it's a horse race unlike Derby. Derby have 20 horses. We have a million horses in a race automatically, any moment. One horse wins, the other 1 million minus 1 will not know that you have won the race if this is true. Get it now? I'm driving this concept home. Why it doesn't know? Because that horse wins. He says, hey, I win. But the other horse says, no, you didn't win because the deformation field has not changed at all under this condition. So the other horse start to win too. Okay? When I say win, I mean the word that we disappeared, I mean disentangle. Look, one layer under this condition, watch what I'm doing here. One layer under this condition, one layer disentangling can never produce your stress dropping. It is all the layers that are disentangling that is producing this dropping. That's almost certain because the force is contributed by the millions. Well, in fact, 10 millions, right? Of course, you normalize that 10 million with your area size of it. Remember, I'm only talking about in 2 dimensions, so this direction, just for the sake of argument, this dimension could be another 10 millimeter, right? So, of course, it's a volume that I'm talking about. Okay? So, I hope I succeeded in telling you that there is a horse race, and we don't have any detailed theory whatsoever in a millimeter range. Oh Lord, it's trying to save. One layer start to disentangle, 2 layers start to disentangle, 3 layers start to disentangle, 1,000, 10,000 layers start to disentangle. But eventually, that disentanglement created a sufficiently large correction to the field so that the field somehow no longer shears homogeneously. Instead, it's sheared. If I know I have to do it differently if I want to succeed in what I'm doing. Instead of shearing like this, the system decides to shear like that, right? And we don't have an answer. Of course, these 2 points are the same point. Of course, we don't have any clue why the system does this in detail. We don't have any prediction about, for example, the location of where this happens. We only were able to argue that this condition could be a condition where shear bending will not occur. When the one layer of slip is sizable, has a sizable effect, we have no idea how it's going to, how this 1 million horses going to communicate with each other and says, oh, this 10,000 horses, you run faster. The rest of says, okay, I can take a rest. I don't need to run that fast. It's like that. We have no clue how they communicate and arrange that, make that arrangement. So, well, if we knew, we would have discovered it long ago. So this is why this initial observation of this was very disturbing, because it resets how we should approach the problem. Okay, I think I really have repeated many of the messages, and it should be clear now. So we can move on to next chapter, chapter 10. I may not be terribly extensive on chapter 10, although the features here are rather unique. But chapter 11, I just want to connect you to what's in the future. Chapter 11 is a case, instead of examining shear, examining the case of extension. And the physics of horse race is the same. And there, we should discuss this in great detail. And there is also a big controversy, big misunderstanding and confusion in the literature. So we'll come to that patiently. And this is clearly one of a core part of the book regarding how we probe our understanding about disentanglement. But we'll start with chapter 10, which is right following chapter 9. I arranged chapter 10 in this space because I sort of want to continue the story of shear bending. In other words, I want to give you just more examples of the shear case before we moved cleanly to the case of extension. Extension is a totally different way of shape changing, of deforming, and also typically involve a different community of people. So the clear separation is useful to have. So in any event, this is the chapter 10 that we are going to go through. I should immediately indicate the connection. So watch out again. So chapter 10, the first topic is about capillary. Well, that should automatically remind you of the wall slip that we did. And indeed, even second topic is still about capillary. So let's remind ourselves what we did in chapter 6. So this is chapter 10. But we are reminding ourselves what we learned in chapter 6 with regard to wall slip, with regard to stick-slip transition, basically by having a capillary. And I told you, this is a good opportunity to learn, appreciate a little more. In fact, this will come back again as well, about capillary rheometry. I will not be completely done with capillary rheometry even after today. But this is capillary rheometry. You have a piston pushing down, either with a constant pressure, which is what we did, because pressure gives you an indication. I can always write the other way better. It should be 4dl. No, cannot be. It's the other way around. It should be L on the top, 4D. This should be right. So the pressure prescribes what is the stress. Oops. I don't want to redo it, so let me just write it back. Oops. Still don't want to redo it. I'm so scared of it. D sigma W. The pressure prescribes what the wall stress is. So because of that, we find if you use how much it comes out for Newtonian material, remember it's 3 over pi 32 d, and then shear rate at the wall for Newtonian fluid, which is fine for us. I mentioned about that. And there's the pressure, and then stick-slip transition occurs in this manner over a particular pressure, and that particular pressure, of course, corresponds to a particular wall stress. So for the moment, I will even omit this star here, just the pressure you apply. Turns out this is the only way to understand wall slip without complications, is for you to get hold of a pressure-controlled rheometer, which we luckily have. Remember, our initial work was done in the mid-1990s. Sounds so distant, 25 years ago at least. But that's all relative, whether it's distance or not. I feel like it was yesterday. So in any case, you get a hold of a rheometer like this, you will find a critical place where I want to emphasize, in case you forgot, where I want to emphasize this point actually is how you achieved limiting wall slip, producing a maximum amount of slip length. Well, other people were not so lucky. They did not have a pressure-controlled rheometer. Okay? Okay? Just a matter of luck. Well, I of course speak this sarcastically. What if you just have a rheometer that's designed by pushing the piston with a constant speed? Okay, it's just different ways to squeeze the material in the barrel out. Okay, right? You have material in there. You're just trying to squeeze them out, and they will come out. It turns out it's very complicated, and of course also very interesting. So you can imagine what happens is that you are, man, if you draw the line, you will see it's just madness. You are basically trying to insist that the material will come out at some rate because you are doing a rate. In fact, if you like, if the barrel has a diameter of dp, then the volume, isn't it? If you forget about everything else, should be 4 pi over 4 dp squared b, right? As a cylinder of diameter dp. That's how much material should come out per unit time. Per unit time. So I know for you, if Q is a new concept, we have talked about once before. It's the amount of material per unit volume. Sorry, let me rephrase. It's the amount of material measured in volume that comes out per unit time. God, mouthful of words here. That's what it is. You may even remind yourself that's piston speed. And this is crazy. Okay, let me tell you what I mean by crazy. If your piston speed is so high, it produces a Q. It produces a Q here, or it produces a Q so low, you produce a Q here. No problem. No problem. You get these 2 points. In other words, this would be the pressure you have. If that's this is called Q1. If that's Q2, you have a pressure of P2 there. No problem. Okay? But you got a sharp transition. In this in-between, you have trouble visualizing what happens. So what happens? The system will try to follow this line if this is the amount of material. But of course, it cannot go to that point because by this point, you already build pressure to make stick-slip transition. But when you make stick-slip transition, you don't have available the volume rate to go there. Right? Of course you don't. Okay? So the system go crazy. System go crazy, watch. Remember there was hysteresis. In other words, remember I told you when you use rate mode, you can lower your pressure, it will still stay on this upper slip range until some moment. So the system, look, the reality is actually very trivial. You have parabolic initially. It tried to deform like this. And all of a sudden, that pressure is too much. It will slip, which means it will slip like this, and then the middle sheared very little. So remember, what I draw this, it will give you a sense of the shear rate that's dropped, and it gives you a sense of the stress that's dropped. And that stress could be now below the hysteresis stress. So the system will come back to stick. Meaning from wall slip, come back to stick, because that's the boundary. That's the condition for stick. Use stick, yeah? And once it's here, since you have a lot of volume, it will try to go beyond that point again. It turns out this material in the barrel can compress and decompress, actually. So it's a very funny thing. It go crazy, the system. It will try to oscillate between stick and slip. And because of the compression and decompression, this is possible because all of a sudden, when you, before you slip, it actually will compress. Now, material is unwilling to come out, okay? Imagine, come on, folks. Imagine I stuck something so that nothing can come out. Then, of course, I compress, okay? So that's like the initial condition. I compress until wall slip occurs. That's like I start to unplug this point, okay? Material will rush out like crazy. Rush out how crazy? More than what you supplied here. Remember, the piston speed is constant. So this thing will just compress and decompress because all of a sudden you are trying to come out faster than what you supplied by. And so this thing just goes nuts. And that's, that whole thing, it just shows it's not a good way to look at this problem of wall slip. So that's what the that's what I observed initially when we first studied this. So for example, that chapter 2, second figure. So if you monitor the pressure just oscillates back and forth. So all these different values are different curves, are the different piston speed that you put, some are low enough, so no problem. Some are high enough, no problem. In between, you get this problem. So if you look at this, there is basically a region of instability where pressure just oscillates back and forth. Very complex problem, and just unnecessary if your goal is to study the nature of wall slip. Okay, so that's that. And any questions? And that was not all for us. For us, we really want to understand some let's call that a prediction. We had an idea if I can watch wall slip taking place as I showed you in the movie. Sorry, did I say wall slip? The shear bending. If I could see shear bending taking place like that, happy. Then we know there are other scenarios where shear takes place. So one of the places you should really have shear is, of course, when you do extrusion. But more importantly, let's see what I'm doing. More importantly, I know I'm carrying you to a very far place already. So very importantly, we are aware that when we extrude, let me explain this experiment that's in the movie. So the material actually was first, this actually is pressure-driven rheometry. So the material was first, let me stop the movie for the moment, was first squeezed to fill the die. Okay? The die is now filled up, just like depicted here. Okay? Then you stop your pressure and come back in an hour. Why you do that? Well, keep in mind what's going on here. The material is rushing, the material is rushing in. Okay, so this, if you like, the material is rushing in. Okay, and if you want to get rid of the effect of this entry effect, if you want to get rid of it, you can. You will just wait for the material inside the die to relax completely. Then it will no longer remember it suffered through this coming in. Okay, so just wait for whatever time you wish. And then you restart your experiment. And the interesting thing, as you can see, is when you restart the experiment, whatever was originally already in the die comes out very smoothly. This is the final photo. This is the final photo. You can see something very remarkable here. Look at what we call die swell. Remember, it has a diameter of d. When it comes out, it can become much bigger, the extrudate. That's called swell. Look at this part. Didn't swell at all, and also smooth. Because this material is already resting in the die for a long while. The effect of the entry is not there, because it's already forgotten. I mean, but whatever is coming new, of course, sees the effect of the entry, and that's the rest. So it proves this is nothing new. Everyone knows this. But the experiment proves that this ugliness has everything to do with material rushing in to the narrow channel from a big open reservoir, right? They were so happy. Remember how happy they are? They are your crystal noodles. They are sitting there relaxed, okay? And all of a sudden, you force them to rush in. Trillions and what? Certainly more than trillions, 10 to the 15, 10 to the 18 molecules being rushed in. Whether they're happy or not, you know how happy they are. They were not very happy being rushed in. So our job was to, since we have this $300 technique, pointing laser, a little objective lens, and a CCD camera, $300 total. Well, our job is to at least peek into, hey, how did this thing rush in? Again, by adding some light reflecting particles to your sample. So otherwise, there's nothing reflecting your transparent sample. If it's dust free, it will be light scattering free, and you won't be able to see anything. So very remarkably, these are the movies. This one is particularly remarkable. So watch, okay? So this is a movie taken at 1/2 of the corner coming into the die. 1/2, because the other half should be symmetrically similar. So this is the middle of the die. Okay? So it's half of the die, yeah? And then this is the reservoir, and it's rushing in. What do you notice? Well, not only it's not terribly regular, right? It's not completely time independent. But what's the most important? What's the feature that you see? Look, there's a place where no, even simpler. Look at this part. It's stagnant. It's not moving. This part is not moving. As if it forms a boundary, but as you said, it forms a boundary on its own. How come? A boundary on its own, as if there was a surface there. Of course, there wasn't a surface. So how much clearer can it be that this is just like shear bending? It defines a place. It's just absolutely remarkable. All this was sort of a prediction for us, so therefore it's even more remarkable and fascinating. So here comes a little bit of the theory and a little bit of the I shall call it the profound theoretical implications. I showed this once to a professor who does computations. In other words, you give him a constitutive model, he will use so-called finite element to calculate the deformation field, such as such a case where material rushes in. Okay? In such a finite element calculation, there are no molecules, there are no physics in terms of what can give you this. In other words, the material. I know the only thing you know, for example, for example, let me drive home to that. The thing we know is Maxwell model, okay? This is Maxwell model. And you can find this, we call it a constitutive equation. And you can find a much more complex one, okay? You can find one, much more complex. That you will use so-called finite element calculation. In other words, solve that differential equation and try to mimic what happens there based on the model, okay? And just for example, this Maxwell model, what are the parameters? Viscosity, well, you may like relaxation time. And in a new model, whatever, there will be parameters A, B, C, whatever you have, okay? Whatever parameter we have. What I want to emphasize is in no cases on Earth today that we have a constitutive equation where these parameters are a function of space. No, never. Remember, the parameters in your equation should be typically material parameters. You know. And the way we previously know how to build it, such equations, are through in a few material parameters. These are just constant. I'm claiming, folks, guys, I'm claiming what we observe here is equivalent to saying that you need a constitutive equation where the A and B and C are spatially dependent. Why I say that? Because here, the ABCs involve untangled state. And here, at the boundary, the ABCs involve a disentangled state. Of course, they are different parameters. And so, I'm saying, this is, I cannot say enough of it, but this is one place that shows us we are so far away from realistically simulate such a case. You can simulate something, but what you simulate is just a mathematical feature of your constitutive equation. They are not real at all, whatsoever. Very, very important. This is we are really talking about start to walk, and we have no idea how to run. I mean, you are just far from getting to that point. So when I showed this to one of my colleagues in doing finite element, he really he dropped his chin, meaning he was really stunned by this. Because he knows this is exactly implies what I just said. That your structural, your structures are not homogeneously the same in space. Okay, that's unheard of. Okay, the only time we do previously, anybody claims, we will treat our material as if it's structurally the same. That's how you have a constitutive equation. By definition, just. Your material is structurally, spatially the same. And of course, by the example of shear bending, we learned the first example, the simpler example of simple shear, that the structures are not necessarily the same in space. they negotiate, that 1 million horses negotiate a fraction of the horses to take the load, the rest don't do anything. So I can get to the book part. So that's why we built such a device, right? You can see that we could look at what happens at the corner, what happens even inside. And this gray area is obviously glass made of. So you have a reservoir pushing through, and then you can shine laser through the glass, and then in the other direction, there is also something transparent for your camera to go in to watch it. So there was a bunch of details in this chapter that I'm not going to go into details. And I want to emphasize some things that was also some result published by my former student. He went on to do postdoc, Puyang. He's now professor at the Delft in Holland. We actually was bold enough to suggest the following. In fact, here probably use the smart pen would be helpful. So I will just do this, then we will finish for today. We actually start to become a little bit bold here. We made the following suggestion or prediction that, so he's using, in this case, he's using a DNA. I know this looks upside down because he's using a DNA. The capillary he achieved is just using a syringe. You know, the one you get a flu shot, the syringe, just push it because it's very much less viscous. So he doesn't care which direction he's pushing. So this is the reservoir side. This is the dye. And we are kind of bold enough to predict that if I can prepare my sample with a slit length that I can prepare and know what it should be, I can adjust that relative to the diameter of, or basically the dimensions around here, such that we can predict that if this is very small, well, it just so happened that the experiment agreed with us. I don't know anything deeper about it, but we actually at least went ahead and tried. There are two conditions: A, B. Right? There are only these two situations that could be interesting. So if you prepare, so the way we do it is rather simple. If you have a DNA solution, if you use water as the solvent, you tend to get a very big B, because remember, B is viscosity divided by solvent viscosity. Solvent viscosity of water is very low. Yeah, very low. Whereas we can also use other aqueous solvents, such as glycerol, or well, glycerol definitely was one of the most viscous. Or you can add some sugar in your water. I would move it up. So you can basically have these two cases. And one was able to show, and of course you can adjust concentration as well, okay? One was able to show that when this is the condition, you have vortices. Why? You predict that? It's because in that case, there will not be a shear plane, shear bending. If it cannot shear bend, then you see the only way to satisfy this continuity is to rotate. Okay, that's why you have vortices. I know I draw it wrong because the material, I draw it wrong because the material is going, it doesn't do. because the material is going this way. So it's basically, it's just coming back, and hit the wall, and then come back. Hit the wall, come back. So that's the physics, in our opinion. Whereas if you want to, you know, it's again unclear whether you can simulate that. But in any case, when you choose the other condition, when B is large, they will try to undergo disentanglement and then form a natural place to go without the vertices. Okay. I think that's all I want to say for today. And I will stop here, actually. And we'll stop here.